Okay, I'm losing my voice, so I should speak very quietly and so on. Okay, very good. So, yeah, if we could increase the volume of this, then I would not need to speak so loudly about that. Try to put like this. Okay. Okay, so let me remind you some of the motivation pictures we drew last time. So I was saying that in the gauge theory, when we start contracting the operators together, we naturally draw pictures where we see all these triangles forming here. So here is a green triangle, another one. So here are all these triangles showing up in the Feynman graphs. And here is another Feynman graph, where you also see 1, 2, 3, 4 triangles coming up. Now, the very same pictures appear in string theory. If I consider here 3 strings, and they are growing, and these lines are the lines of the closed string coming from the blackboard. Then, and there is one from infinity that is coming, and I find these critical lines, these critical points, and in this way I obtain this graph, whose dual graph is exactly the graph that I draw in the gauge theory. The fact that here in the gauge theory the fundamental object is the triangle is the statement that these zeros here that form these bifurcations will lead to always bifurcations. They will be cubic vertices here. And that's the generic situation. So I'll have cubic vertices here, which means a triangulation here. And then, in this dual graph, we said that each line I can interpret as the number of propagators, so of course they are conserved. So the ones that go up diagonally or left, they add up to the length of the operator, which here is the statement that this closed string, when I think of it, when it grows all the way to these 3 critical lines, its length is split into the length L, L prime, and L prime prime of these 3 segments that need to add up to the same thing. Now, there is also some mathematics that goes with it that I mentioned by words, and that I recognize that was a bit sophisticated, all this blah, 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 which is irrelevant for these pictures. It is just to motivate a little bit and to say that such graphs always exist and that the map is unique and so on. But the picture is enough so that we see these triangles coming about. It's also nice to see that because we have 6 lines, but we have 4 constraints that the propagators are conserved, we end up with a 2-dimensional sum. And 2 dimensions is nice, because that's the dimension of the moduli space. We also integrate over a complex position z of a puncture when we fix the other 3. Now, more generally, what happens is you take this puncture and you start moving it around. And as you move around, you deform this graph, so you are changing these lengths. So far, so good. But eventually, you move it a lot. And when you move it a lot, you can get to this situation, see. And here, if you draw the corresponding graph, you see this graph is not the same as this graph here. The dual graph now is this one here. You see that this guy, it has 2 faces which are neighbors, but this guy has 4 getting out of it. So you can see that the dual graph, this line has 4 propagators getting out, and this guy has 2 propagators getting out. Okay? But that's another graph that you draw in the gauge theory. And again, you have 6 lines in total, 4 constraints, so a 2-dimensional sum. So as you integrate over this, you move the puncture everywhere. Eventually, the graph jumps to this graph, which means that in the gauge, it's the analog of in the gauge theory, organizing your graphs like this. First, you write all the skeleton graphs, which are these cartoons, this picture or this picture. And then the second step is, for each skeleton graph, you sum over ways of distributing the propagators in the skeleton graph, which is like visiting the vicinity of the moduli close to this configuration or close to that configuration. Okay? And then we also said that in practice, when we want to glue 2 objects, we have to sum over what flows in this line, which means inserting a resolution of identity. So in practice, because we have 6 lines, for example, for this example, we would get 6 sums when gluing together these hexagons. So I remind you that these triangles, we think of them as hexagons exactly because of these cartoons here. When we are cutting, if we have to remember that the operators that we insert are really some small circles. So when we resolve these insertions, we see that there are 3 small segments here. But as Abhijit pointed out yesterday, there are 2 types of edges. There are these small edges, which were originally the operators, And now we did something very tough to an operator. We had an operator and we broke it in two. That's not something we normally do in quantum field theory. In quantum field theory, we say, oh, there are some guys to the left, some guys to the right. I will put a surface here separating nicely things. We don't start putting surfaces that go exactly through operators unless we are a bit deranged, right? But that's, of course, exactly what we are doing here. Okay? So these physical edges, it's really you add a closed string and you cut it in half. Now you have two halves of closed string, and here it is. And then we have these edges, which are the mirror edges, where we glue the hexagons, where we insert the resolution of the identity for gluing the edges. So when you insert the resolution of the identity, you sum over all states that you organize by how many particles there are. 1 particle, 2 particles, 3 particles. And then what you have to compute is expectation value of the hexagon in each of the states. So that's not the operator, that's already the expectation value of the operator. It's called the form factor. Okay? And so the basic steps we have to do is find the hexagon form factors and understand how to glue them, and hopefully learn that once you look at the expression for their gluing, there is some other structure and we can do even better. But at least that would be the strategy right now for constructing complicated topologies which could lead to these higher correlation functions in n equals 4.
So, should I be worried at all that the moduli on the field theory side are discrete and the one on the string theory side are continuous? Should I expect this to only work for very large L or not?
No, the claim here would be the map is not really obvious. In the integrability, in these cartoons, it's hard to disentangle, say what is integration over moduli and what is summation for a fixed moduli over the string vibrations. Both are together in the path and it's hard to separate both. So we could say several words. We could say, first we sum over the discrete sets of the moduli, but then for each discrete set, we are still summing over all these mirror particles that get out, and they are kind of covering the vicinity of the moduli, and that's how the string, the continuous integration would emerge. Now, to see something really more direct, where these sums, I replace them by integrals rather than sums, we don't know how to do. But perhaps it's possible to just write some integral with a delta function, then the delta function disappears eventually. But that we don't know. Right now, it's true that one is continuous, one is discrete. Yeah, it might be related to some kind of light cone gauge choice, where because the sphere is periodic, momentum is periodic there, and maybe it's possible to lock target space and worldsheet in some way. But right now it's true, it's a distinction. We have a continuous moduli here and a discrete moduli there.
Could you say again why there was this pi conical axis?
Okay, so let's say a little bit about that. So the idea here is that this is the state, right? And if you look here at this cylinder, it's particularly clear here. Here you have, say, the future, and here you have a weak rotation of the state. It's a state perpendicular to it. It's exactly like what Shota was drawing, this cylinder, and saying virtual particles could go perpendicular to it. So these virtual particles are the weak rotation of these physical particles. I just put them here. But now, how many weak rotations do you need to do to go back to yourself? You do one, then you do another one, 2, 3, 4, 5, 6. So you need to do like 6 weak rotations to go back. So it's as if, in this Euclidean picture, you have to go around not 4 pi, but 6 pi. Not 2 pi, sorry, but 3 pi, which is 6 times pi over 2. So, and that you could do by thinking that I put some branch point twist operator that inserts half Riemann shit. Okay? Or in other words, it puts some conical excess pi. Okay, so these operators, people consider them in some other contexts, some very similar operators, and are called branch point twist field operators. So let me give you an example of where these operators would be useful.
In the hexagon, why are we only inserting operators on one edge? In general, would the form factor be different if there were insertions on all the 3?
Yes, I will comment on that. So indeed, that is a very good question. Why am I putting 3 excitations here and not 3 here, 2 here, and 5 here? Indeed, that would be the general setup. I can already anticipate that the reason is, if I know the ones with everyone on one edge, I can then do crossing symmetry to bring things to the future and to the past. It's like in scattering amplitudes, we can think everyone is incoming, and then we do crossing symmetry to put some particles to be outgoing. Okay, so it's just a generalization of that for this case. Is it clear? I'll explain a bit later. So suppose I want to consider a path integral where I put my field, my field, which lives in 2 dimensions. I put it on a Riemann surface, for example, where there is, say, a cubic square root cut, which means that when I'm here, when I go here, I get out here, and I go here, I get out here, and I go here, and I'm here. Okay? And I want to do my path integral over fields phi, e to the minus the Lagrangian that depends on phi, on this Riemann surface that could be parametrized by m, I'll explain what m is, and the position of these 2 branch points, x1 and x2. So m here would be how much conical excess each operator puts. So I want to say that this generates an m-gon. So in other words, here, for example, if you go around this, you see that instead of having 4 regions, you have 4 plus 4 plus 4. So in this figure, m would be 12, for example. Because I go around this operator, I have, instead of having 4 futures, I have 4 plus 4 in the second floor plus 4 in the third floor. Okay? So m would be 12 for this case. Okay? And of course, if m is not a multiple of 4, these pictures, I have to think of them as some kind of analytic continuation. But the way I'm drawing it, I'm implicitly, let's implicitly for now say that m is a multiple of 4. Okay? Now this operator, this you can think of this path integral as saying that this is nothing but a path integral where I consider the path integral just in the complex plane, but the price to pay is that I will introduce some operators, phi 1 and phi 2, that if you want are defined by the following condition, that I will now have, instead of having one field on the Riemann surface, I will now have J, where J runs from 1 to m over 4, in this case from 1 to 3, there are 3 copies. And I think that this phi j was what was before phi when x took value in the jth sheet. Okay? And then what's the condition I do on my path integral? Is when my field phi copy number j is here, x plus I0, it glues here on this side with phi on sheet j plus 1 right below. Okay, and by these arrows, I mean an equal sign on the boundary condition. Okay, and then I will do a path integral over all these fields, phi 1 up to phi m over 4, e to the minus the sum of these Lagrangians for each field. Okay, and this, if you want, is how we would define the expectation value of these 2 twist operators that create this conical excess. One inserted at x1 and one inserted at x2. And if I consider now the expectation value of something, this is the expectation value of something. Okay? More precisely, if I want really this to be expectation value, I should divide 1 over the partition function, 1 over the partition function, and then what we would write is this divided by the 2-point function phi, phi. Okay? So from this, let's suppose, to get some intuition about these operators, let's consider them. Okay? So before I consider them in a conformal field theory, which is what I'm going to do now, let me just mention that you see why this could be useful, because this identification, this thing that you say, I do my path integral, I produce some functional here, and then I multiply it again, and I do the path integral again, and again, and again, and then I close, is exactly what you would do to compute the trace of some density matrix, where you integrate the path integral and you multiply these density matrices. And here we do it n copies. So if we could do these computations for arbitrary n, then we can take some derivatives and then to 0, and we get this entanglement entropy and so on for this segment. So this is why these operators first appeared in this context. Okay? So just as an exercise to get some familiarity, let's suppose we are in a CFT, and let's verify that these operators would be operators that would have a dimension like this. Okay, so that's what we want to do now. Let me just show you how this comes about. Okay, so this would be the dimension of these operators in a CFT where C is the central charge. Okay. Because what I want to do is first let's find this result, and then let's start going to not a CFT, a free massive particle, and in a particular limit then we want to recover this result again. But for now let's just compute this here. So for that we can do the following. Let's consider the expectation value of T, of the stress tensor, at a point x that is in the jth sheet, in the theory computed on this Riemann surface M, which had M with M x1, x2. Right? Good. So by definition, this is equal to what? Well, by what we just said, this is nothing but Tj, where Tj is T, was T at the jth sheet. In other words, it's T of the original theory computed with the copies number j, and then phi 1, phi 2 evaluated in C divided by phi 1, phi 2. By phi 1, phi 2, I mean phi at x1, phi at x2. Okay? And this is phi j, it's copy number j. If I were to sum over all copies and they all give the same result, it would be the full stress tensor here on C. So on the other hand, this computation here is 1 over n times the same with T. T phi phi over phi phi. Just because I have one copy here, and each copy gives the same thing. And the n is m over 4. There are m over 4 sheets. But on the other hand, what we can do, if we are in a CFT, this is where a CFT is entering, we can apply a conformal transformation that sends this configuration into the sphere. So that's easy to do. So we can just write something like Z. So if this is the W plane, let's map a transformation that going around m over 4 times this point, you do a turn in Z. So you do something like Z equal, let's do it, W minus x1, W minus x2 to the power 4 over m. Yeah, that looks good. So when m is 8, it's 2 sheets, so it's a square root, you see. When m is 8, you go around twice. And then, sorry, this is not equal to this. This is the transformation we do. This is equal to dz dw square, right, just from the change of variables, times the expectation value on T on the sphere. But this is 0 by translation invariance. There's nothing here. We got rid of this. Plus, this is how stress tensors transform, right? There is a C over 12 times the Schwarzian. So this is equal to C over 12 times, so the Schwarzian, I remind you, is just these 3 derivatives, 1 derivative, some combination of derivatives of Z, And now all you have to do is compute these derivatives for this function. Right? You just need to compute this derivative. So the result would be c over 12 n squared minus 1 over n squared x1 minus x2 squared, and then double poles at x1 and at x2. Sorry. Okay? And now you just need to compare both equations and recall that you have this word identity for the stress tensor, that T phi phi is equal, which appears up there, right? T phi phi is equal to the dimension of the field, right, over W minus x1 squared plus a single pole, but a single pole is not important. We can read off the dimension from the double pole. D dx1 plus the same thing for 2 acting on the 2-point function. And now you read off the double pole. You see the double pole when W is x1, this term cancels this term, and I get this. And this is almost what I wrote up there, except for a 4 over m, that is exactly that 1 over 4 over m over there. Okay? So we get delta equal to what I wrote there. Okay? So that's how we compute the dimension of these operators. That's right. So this h is half of this delta. Yeah, I think there is there's probably 35. Yeah, the h delta, yeah. No, there is both. So the correlation between 1 and 2 is the distance x1 minus x2, really the Euclidean distance, to the power 2 delta, where delta is what I computed up there. Okay, good. So now this is a result to keep in mind, that dimension that I wrote there. And now let's study a little bit what happens if we play this game for a free massive boson. Not the CFT game, of course, but the game of considering these branch point twist operators for a free massive boson. So for a free massive boson, let me write for you what this object is. Namely, I take an n-gon, it could be an hexagon, but I'll draw an octagon so that we don't get tired of drawing hexagons all the time. And we have some operators here. Okay? So this is a free boson, so these guys would be parameterized by some rapidities, theta 1 up to theta n, right? So the momentum is m of an excitation is m sinh of theta, the energy is m cos of theta. And then this form factor, that again I would write as saying I have vacuum, I have my operator that generates some conical excess, and then I have my in state, theta 1 up to theta n. And someone already asked, why am I not putting particles on all the edges? And I will mention soon that it's because I can move them around with crossing symmetry. So let's put everyone on one edge. And the result for this computation is the following. Let me write you the result and then we'll discuss it. It's equal, this is just, again, this is now for a free massive boson. And this is equal to a sum over all possible pairs of rapidities you can make, and then product, it's like weak contraction of all the rapidities, f of theta I minus theta j over these pairs. So you sum over the pairs and then you sum them, where f is a function that depends on m, what m-gon do you want, and for an m-gon, I recall this is m-gon, this Fm of theta is equal to this expression, sinh theta minus I pi over m over 2, sinh theta plus I pi over m over 2. There is some m over 2 here, and there is some sine of 4 pi, no, pi over m. Let me check. I prepare things. I feel like this reality show people who will get a television. Okay. Yeah, I have a 4 here, but I doubt this 4. But okay, maybe it's correct. We can check later. Okay. So I'm more interested in understanding the properties of this object than in telling you how we could explicitly compute it in a free theory, because as you will see, we will now verify what properties this object has, and in general what we do when we have an integrable theory is use those properties to bootstrap and to guess the object, because we cannot just compute it exactly. But in a free theory it's easier, and you can also compute it exactly, because you can basically generate this conical excess by saying that I have my operator, it goes around, and the difference between when it was below and above the cut is like inserting a copy of the complex plane, right? So it's like saying that on that line there is a big conformal transformation that is some integral of the stress tensor. So in this case, for the free theory, you can write some explicit expressions for these operators as, morally speaking, something that inserts some big conical excess. I don't know, something like this. It exerts some big conical excess, some integral of, say, you put a bit of space times r, something like that. Morally speaking, it's something like this. And then for the free boson, this is just quadratic. You can just put excitations, do weak contractions, compute, and you end up with this result here. But in practice, this kind of a representation it's too complicated to work with, it's useless. But it gives you the intuition. It's like you go around, and what's the difference between above and below the cut? It's if you want to go from above to below, you have to go around in the second sheet once, for example. And how do you do that? You put this integral that sends you around by an angle that you need to. Okay? Anyway, this is a side remark, that we have a luxury that for free bosons and free fermions we can use such representations and compute. So there is a very similar expression for free fermions, but this one already has a lot that we can play with. Okay, let's see who our guest is going to be. Okay. So I want to now check some properties of this object. Let's verify some properties of this object. The first one that you notice is that this f is an even function. F of theta is equal to f of minus theta. And then it has the implication that this form factor is fully symmetric in any permutation of the thetas, because it's either symmetric because f is even, or because you relate two terms in the sum. Okay, so this f is just fully symmetric. So in particular, but the relation I want is the following, is that this form factor obeys this equation. I have 0, my field phi, m over 4, and if I swap particle 2 and 1, and I don't touch the other ones, theta 3 up to theta n, I get 1 times the form factor 0, phi, where 1 and 2 are in the same position. And I can do this for any consecutive pair, because once I do for any consecutive pair, then I can do for any thetas. But for any consecutive pair, I can do this. Okay? The interpretation of this equation is that this one is the S matrix of the free boson. And what this equation is saying is that if I swap two particles, I pay the corresponding S matrix. But here, it's just a free boson, and we get a 1. Okay? So it already tells you that if you want free fermion, you probably want some odds f, and something like that. And indeed, you can, the free fermion, there is some extra sinh theta here, and this is a Pfaffian instead of this object that's called an Affian. And you can generalize a little bit. But for free boson, this is the S matrix of the free boson. And this picture is just a picture that if I have my object, I'm drawing the same object in this picture, and if I swap two particles, I pay an S matrix. Right? So if I have here theta 1 and theta 2, here enters the S matrix, and here I have theta 1 and theta 2. Okay? So the object, okay, or in the picture I wrote differently. You relabeled 1 and 2 in both sides, and it's this equation. Okay? That this is equal to this. 3n. Okay? So 1, 2 is equal to 1 to S matrix of 1, 2 times of object with 2, 1. Okay? So they are just the same. So this thing is what's called the Watson axiom. That's the first axiom that these objects should satisfy. Let's check a second axiom that we can check. We look at this expression and we see that f is even. Both. Both. This is the most elementary axiom in this, but it's a person. It's a person. And now the second thing we see when we look at this f, it's not only even, because this is mapped to this when theta goes to minus theta, but it has a pole when theta is I pi. Right? So this function clearly has a pole when theta is I pi. So we can ask what happens to the residue of my form factor when theta 1 becomes equal. You see what appears here is theta 1 minus theta 2. So when theta 1 is equal to theta 2 plus I pi. So let's try that. Okay, and I want to put here the full form factor. Okay, I think you forgive me, I'll just put form factor. Okay, it's what is this thing here. What happens when we do it? Well, we sum over all pairs, and the residue comes only when we have f in when we have one pair, it contains the rapidities 1, 2. Then when it does, the residue of f, it's normalized such that this residue is 1. So that's why this normalization is nicely put here. So what you are left is with the other thetas after you do that. So you see that 1 over I times the residue of this form factor is equal to the same form factor where now particle 1 and 2 disappeared, and we have particle 3 up to particle n. Okay? And the picture here is that what happens. So there are two pictures, or a few pictures we can draw to associate to this equation. But one picture is the following, is that I have my operator. Okay? So I'll draw two pictures that correspond to this. One is the following. We had our particle theta 1 here, but we did theta 1 goes to theta 1 plus I pi first. We shifted it by I pi. So when we shift theta 1 by I pi, theta 1 goes to the future here. Now this is theta 1 plus I pi over 2 twice. We do 2 mirror rotations. Okay. Remember that under this, P becomes minus P, energy becomes minus energy. You are sending into the future. Whereas if you do a shift of I pi over 2, P becomes energy, energy becomes P. You are just rotating by pi over 2. Okay? And theta 2 remained here. And then the other guys are here, theta 3, theta 4, and so on. Now what can happen is that this operator can go here, and then they can both go very far away so that they don't see everyone, and they just decouple. Right? This is just a statement, they can be there. So indeed what's happening is that when theta 1 goes to the future, then when theta 1 is equal to theta 2, this is the momentum space version of saying the position goes to minus infinity, it isolates that singularity. And that's just a decoupling of these two particles that go to the left, and they disappear, and they leave the other particles. So they are just decoupling here. Okay? So that's just, they just move to the left. This is just these two particles. They move to minus infinity and decouple. The other picture I could have used to explain is to say that no, don't move it to the future. Leave it here, but remember that this is a theta 2 and this is an antiparticle, so they just explode and annihilate. and disappear. Like particles and antiparticles, they annihilate, and they can just annihilate and leave the rest. Okay? And then this is just like particle-antiparticle annihilation. They just annihilate and go away. Okay, so this is what's called, this second is called the decoupling axiom. And finally,
does the decoupling axiom only work if they're at the end? The two are at the end?
right. In general, they would only, so how would I do it if they are not at the end? I would have to combine first with this axiom. So if I want to decouple 3 and 6, the first thing I do is I use this matrix several times to bring them to the end, and then I bring 3 to the future, and then they decouple.
The putting the particle in the future thing makes sense from that point of view. Like it's clear that they don't decouple if you do that, it just makes sense.
Right.
But the particle-antiparticle thing is a little less clear. Like if you try to if you make particle-antiparticle in the middle and you put them really close, they don't precisely annihilate. You still pay some S matrices. So like, what's the picture for that?
Once they decoupled here now, right? They are not in the equation anymore. Now I can do whatever analytic continuation I want. It's like they already disappeared.
Yeah, I agree.
So mathematically, they could have disappeared anyway.
I see mathematically how to compute it. I'm just wondering, like, if you want to decouple two particles in the middle, and you imagine that one's an antiparticle and one's a particle.
Yeah. No, I agree that mathematically we understand how to do it, but physically, to be sure, it's better to decouple it on the side always. But let me make one more comment about that, which is that you see that we have a pole when θ1 is θ2 plus I pi, or when in the other one when it's minus I pi. And typically what happens is that if we have a polygon, now, let me draw it in the polygon picture. What's happening is that I have a bunch of particles. Let's say I have here some particles, and one of them I move. So let's first do the usual one. I take this one and I move here. Now this particle is here. And now this particle and this particle can just go very close to this side, right? Which is, remember, this is infinity, right? So they go very to infinity and they just decouple. What could also happen is that this particle could go on the other direction, and then it's this side that they could decouple. Okay? So in general, you have really two separate decouplings. There is the left decoupling and the right decoupling. If I want to decouple this particle with this particle on the other side, it has to pay first a bunch of S matrices to decouple. This decoupling axiom, for local operators, it has both terms at the same time, because you just have a local operator, the particle goes to the future, and there's no such thing as the left and the right being so different from each other. And then on the right-hand side of the decoupling, you get two terms. One, which is this, and another one, which is a product of S matrices, which is it has to first go past the particles. But this kind of form factor twist operators, they nicely simplify this, and you just get either the left or the right decoupling. So there are two poles, this one and this one, which are separate there. Okay, so that's the decoupling axiom. And finally, we have another one, which we see that our function f, it has some natural periodicity, right? It has sinh of theta over this m over 2. So this function f, for example, f of theta plus, I will write an equation, I pi over 2. So let's see, I pi over 2 is one step, and how many steps we do if we are in an n-gon? I want to do m steps. Now I go back to the same position. But after I go back to the same position, the particle swaps its order, so this should be f of minus theta, which for us is just f of theta times 1, but that's because the S matrix is 1. Otherwise, this is what I expect. More generally, what I'm saying is that I take a particle, I move it around the world, and when it gets back, it's on the right. So more generally, the equation is that if I have my form factor, and θ1, I do m weak rotations, and then I have θ2 up to θn, what I should get, and what we can check we get, is the same thing, where now theta 1 is at the end, because it just moved all the way around. If I apply it for two particles, I get that theta 1 minus theta 2 should become theta 2 minus theta 1, which is a flip of sign. And then because the theory is free, it is just the same as f of theta. And that's another nice equation that we can check that it nicely works because of the periodicity of this fundamental building block. Okay? And this we would call the monogamy axiom. Okay? So the picture here would be, I take one particle, I move it around, and I get the same thing, but where particle was on the left and it ends up on the right. Okay. So now I would like to do two computations to these objects to give us some experience of gluing these objects. So we computed this form factor. Now it would be nice to use this form factor to compute some correlation function exactly to see how this gluing works and what happens when we put two polygons together and start gluing them. Okay? What time is it? There is a clock there. So that's 11. How much time do I have? Okay. While David comes. Half an hour? Okay. Perfect.
Break, and then you have another hour and 15 minutes.
Very good. So half an hour until the break, it's perfect. This is exactly the time I think we need. Okay. So there are two computations I would like to do. One is the following. Let's imagine we have, for example, an hexagon, or more general, an hemgon, and we want to glue it. So we want to put another one here, and we want to glue it. And I want to sum over what flows between this operator and this operator.
Sorry, that operator is a twist.
This operator is a twist operator. This is a twist operator, phi m, and this is another twist operator, phi m, and they are separated by some time x. Okay? And now I'm gluing them, and remember each operator generates some conical excess, and I'm thinking of the two operators and I'm gluing them. What do I expect when I'm very far away? I expect that the conical excess adds up. I'm adding one operator adds some conical excess, the other adds more conical excess. I should go around and see even more conical excess. So that's the kind of thing we want to see.
So is this m then the one specific for this particular polygon, or it could be different?
It could be different. Right now I'm doing m equals 6, m equals 6 in this picture. But this could be, I will keep m arbitrary. It can be anything.
But then I will not draw hexagons?
Yeah, then you would draw more edges here. So in this picture, m equals 6 for the bottom and top. Otherwise, we would have both. We would have a different one. Okay, and one computation we can do is, for example, suppose, so let me first make a comment, that this, in this picture, it looks like this is some sort of octagon after gluing. Right? So in other words, we had 6 edges and 6 edges. We glued, and now we get 3 in the bottom, 3 in the top, plus 2. And that's fine. If you have an hexagon plus an hexagon, remember each hexagon inserts a conical excess pi. Pi plus pi is 2 pi, so the full object inserts 2 pi, which is exactly an extra Riemann sheet. It's an octagon. Right? So this looks like an octagon. This would be what we would get, for example, if we had our pair of pens example. And you remember that a pair of pens, we said, if we cut it like this, and like this line here, we get 2 hexagons. But if I sum over everything in this line, that is, if I glue these 2 hexagons, then if I cut this open, what would I get? If I call this A, then I would get a picture. This is B. This is the other part of A that got cut. And this is C. So if I only cut twice the pair of pads, I would go to this octagon picture. We got to the 2 hexagons because we cut 3 times. So this would be how we would, for example, do the sum of the particles here. It's the analog of the exercise we are doing there. Yeah.
Am I correct to think that in the CFT picture, this gluing is happening at infinity, right? It's after some infinite amount of Euclidean time evolution.
No, it's the extreme opposite. What we want to do right now, what I want to do now, is consider these 2 points to be close. Because then you see each operator, you imagine like a cone. It's like each operator inserts a bit of conical excess. And I have a cone here and a cone here. So in total, the total conical excess far away just adds up. So you bring them close, and what do you expect? You expect to find some kind of OP of these operators, where if I have phi m times phi m, I expect to find in the OP of these operators something like phi to m minus 4 plus other stuff. Right? And what we want to do is study the short distance. We want to study the some short distance examples and look for signs of this OP that we expect when we join these 2 twist operators. Okay? Good. So let's do that. So the first exercise I would like to do is to imagine that we have one particle, say, here, far away, one particle inserted here, far away, and we want to glue to obtain what's the effective object that I get when I have one particle here, one particle here. Okay? So what do I expect is that after summing over all excitations I can put here, after summing over all these excitations, I should get an effective object that couples this particle to this particle here. Right? So that would be an example of some computation of preforming this sum. So just to be a bit more explicit, let me remind you of something, that when we have our object here, we had, for example, this object here. This was just our fm of theta 1 minus theta 2. That's what this object is, theta 1, theta 2, for a given polygon M. If instead I want, for example, to put a particle here and a particle here, a theta 1 and a theta 2, notice what I could do. I can take, for example, theta 2 and do 1, 2, 3 rotations in this direction. So this could be f of theta 1 minus theta 2, and let's put here 1, 2, 3. Let's put here a 3 gamma, where this notation is just theta 2 minus 3 times I pi over 2, 3 weak rotations. Okay? And this is how I would take this particle and do 3 weak rotations to bring it up there. Is it clear? Good. Let me just make one comment, a mathematical comment, which is the following. This guy has some Fourier transform that we can compute, f tilde of omega. So if you compute, it's the following. It's minus sinh of n minus 1 pi omega divided by sinh, m over 4 minus 1, m over 4 pi omega. Okay, you can just compute this Fourier transform and you get this. Yeah, it's either this or the inverse of this. Let me check. It's correct. So you get this. And if you Fourier transform this object, so this is the Fourier transform of this function of theta. And here we have to be careful, because implicitly in writing this, we are saying that this object is the integral of this function times e to the I omega theta, where we integrate over the real axis. If we do this, it's like integrating at a shifted value. Naively, when we shift in Fourier, we just multiply by e to the omega times the shift. But we have to be careful that there are these decoupling poles. So as we are shifting, we pick these poles. So I would say that for these guys that are far away, I would call this Fourier transform f tilde hat. Okay? And it's not just this function multiplied by a shift. It's this function multiplied by a shift minus some term from removing the pole that you would get if you were naive. Okay? But it's a very simple Fourier transform. You can compute again of omega. So this object, it's in the exercise you are asked to compute this Fourier transform and this Fourier transform. They are very similar to each other. Okay? But now we take them as tools because they are going to simplify a lot the computation we are now going to do. Okay? Okay, good. So let's start this computation, where again, let me draw it once more. I'm gluing these two hexagons. And I have one particle here. By here, I don't mean, it doesn't need to be exactly opposite. If there are many edges here, it just needs to be somewhere far from the gluing part, such that I avoid these decouplings and ipies. It's somewhere in the bottom, far away. If there are 20 edges here, it's even better. It's somewhere in the bottom, doesn't matter where. Right? The Fourier transform of this position, yeah, just that. And here there is another particle. And now there is I insert a complete base of states. So I have to put here an odd number of particles, and I have to sum over this number of particles n that I put here that are odd, because each form factor is non-zero. I did not write, but it's a free boson. It's non-zero only if the number of bosons is even. Okay? And there is 1 here already, 3 here, it's 4 in total. And in the top, 1 here, 3 here, it's 4 in total. Okay? So now, let's write explicitly what it is. So the first term that we get is when we have 1 particle and then 1 particle on the gluing line. Okay? So this would be the integral over that particle, d theta over 2 pi, e to the minus the mass times the length, that the separation of the two twist operators, like I was saying. They are separated by some length x, by some time x, times the energy, which would be cos of theta for this particle, times the form factor for a particle in the bottom, theta 0, interacting with theta 1, times, interacting with theta, let's put theta 1, times f of theta 1 minus theta 0 at the top. Top, bottom, where this is theta 0 bottom, and this is theta 0 top, and this is the rapidity we integrate over. This would be theta 1. Yeah?
I'm missing something basic. You're
Yes.
thinking of these as path integrals. These pictures are path integrals being gluing together as like gluing, like the original pictures that you
I'm just doing this. So I have 0. I have my operator m over 2 at x. I have my operator here in minus infinity. Yeah. Yeah.
So every edge corresponds to the
Yes.
0 value.
Yes. So everything is in the vacuum, and I have to compute this object here. Now what do? We insert here the resolution of identity. What's this resolution of identity? It's the sum over n. Sorry, so I said something wrong. In this picture, I don't want to put a vacuum. I want to put an excitation here, theta bottom at the bottom, and here theta top at the top. But okay, apart from that, it was correct. But this identity, it's what? It's sum over n, 1 over n factorial, because all these particles are indistinguishable, integral d theta 1 up to d theta n, and then states theta 1 up to theta n, theta 1 up to theta n. This will be what I will do for resolving the identity for the free boson. Any number of particles that I can put. Then when I put it here, this object here gives me the form factor. That's what I wrote here. The second one almost gives me the form factor, but there is an x dependence. But I just translate, and that picks me this factor here. And after I translate it, it's just again a form factor. Okay? And that's how this result becomes just an integral d theta 1 up to d theta n, 1 over n factorial, sum over n, and then an exponential of minus mx, the total energy, which would be a sum of cosh of theta j. That would be the total energy. Here it's for one particle. And then this form factor that I wrote for the bottom times the form factor for the top. Okay, any question? So let's see graphically how to represent this first term. So graphically, this first term is just, I have a theta 0, I connect with an integration particle, and then I connect with a theta top. I start with the bottom, and I integrate over the middle particle, so it's just a convolution, 0 with 1, 1 with 0. Okay? So this integral we could compute. Of course, if we know the Fourier transforms, it's very easy. Just multiply the Fourier transforms. That's the result of the integral. If you want to study the limit, I forgot to say, what we want to do is study the limit where this distance is going to 0. We want to study the short distance region. Then we are just doing a usual convolution. If we have the results in Fourier that I just told you, we can just multiply in Fourier and then go back again. Is it clear? Yeah? So this one is easy. Then the next term would be when we have here, when we sum over 3 particles. And now you see that in the top, let's focus first on the top. This particle could contract here. This is one pair that we have to sum over. And then these 2 integration particles could connect like this. And that's one option. And the other ones are all identical by relabeling of the particles. But now that I chose this, I have to fix the bottom, what I do with the bottom. And with the bottom, this particle could, for example, connect here. And then these 2 could connect like this. That's one option. But there are also other options. Or I could have this uglier one in the sense that they would form this disconnected bubble. Right? So this bubble here is disconnected. And if we want to get rid of it, it's enough to just remember that we are summing over this particle. Let's divide by 1 over z, where I put vacuum and vacuum here. And then this just removes these disconnected parts. So let's ignore this. These disconnected parts we kill. And what we are left here, you see, is convolution, 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 convolution. The only thing I have to be careful is that the convolution I use here is this f hat. The convolution I use here is this f hat. And the convolutions I use here, because this connect to these guys that were far away, was this f tilde hat. And here f tilde hat. Okay? And that generalizes. I can do many particles. And the conclusion, if I do all the combinatorics, is the following. Is that the result of this sum, so if I call this sum here hashtag, the result of this hashtag when mx goes to 0, it's just a bunch of convolutions, and it's equal to 1 plus this convolution plus, as we said, this one plus this one plus dot 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 with coefficient 1. So it's a nice geometric sum that gives, in Fourier, it will be just the Fourier of these 2 external guys, this f tilde hat with m, and here 1 minus, there are 2, here there are 4, and so on, so f hat square. So this would be the result in Fourier And then what we want to do is inverse Fourier transform this expression, and this gives me my expression of theta 0 top minus theta 0 bottom. Okay? So you can just compute this. These are just some I wrote somewhere, it's just some sinh over sinh. And nicely, what you see if you compute this ratio for m is that this ratio is nothing but f tilde hat of 2m minus 4. Okay? But this is exactly what you wanted. We joined the operators, and now we have a transition of a bigger polygon. That would be the transition of the bigger polygon. Okay? So therefore, this function here, the result is just f for the corresponding 2m minus 4 of theta.
So you're saying the UP is regular, there's no singularity when x goes to 0?
So here, I'm dividing by the singularity, so I'm just studying the effect of having these two operators here. And when I'm doing the OP, I'm just seeing the dependence on these two rapidities, that it is that of a twist operator with the right conical defect.
So the singularity as x goes to 0, I could predict just from the dimension.
So let's now check that. Okay? So João is saying that we should also see that there is a singularity when these points are coming together. And that's exactly from these disconnected parts that I ignored. So let's do it more carefully. Let's do another exercise. But this one, I want to emphasize, it's already nice. So what we see is that if we put some conical excess around the point and around the nearby point, and then put a particle here and a particle here, a theta 0 and a theta 0 prime, they feel indeed just a bigger conical excess. And that's exactly what we would expect as we join these operators. Okay? But now, let's really study what happens if I just compute a two-point function between two twist operators. So now I repeat the same picture, but I'm not going to put anything in the bottom or in the top. I'm just going to sum over particles here. And now, because I don't put anything in the top or in the bottom, this number now is even. Before it was odd, because one was in the bottom, one was in the top, so I had an even number here. So now this exercise is a bit different, but very similar. So this separation is again x, and this is even, and we sum. So what we have to do, the first term is 1, nothing, when you have the vacuum. The second term is just the loop that I was disconnecting before. When I put two particles, the form factor for each is an f, so I have this loop. This loop comes with 1 over 2 factorial. The particles are indistinguishable, so I put a 1 over n factorial. The second term is plus 1 over 4 factorial. And now I have two possibilities. I have a disconnected loop, and I have a bigger, loop. Okay? Is it clear that we have these two possibilities? And they come with some coefficients. Okay? Just with contractions. And so on. And you can easily see that this becomes the exponential of the sum over n of 1 over n times a loop of this n, times a loop where there are 1, 2, 3, 2n lines, a loop of length 2n. Okay? So by this, what do we mean by this loop of length 2n? So far there was no approximation, no short distance, nothing. This was exact so far. So let's just do a computation to see. what should this be? So this loop, so let's call this cycle of length 2n. So this cycle of length 2n is just the integral d theta 1 up to d theta 2n over some 2 pi to the 2n. And then the energy, e to the minus mx times the sum cos of theta j. And then just a loop, f of theta 1 minus theta 2, f theta 2 minus theta 3, dot, 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 f of theta 2n minus theta 1. Ah, yeah, that's correct. Okay, and now we want to send the short distance limit when these mx are going to 0. But notice that if I just put this equal to 1, I get a problem because this integral is invariant under translation. So if I just remove this factor, the integral over the overall translation of the variable is going to give infinity, right? So I can think like this. I can think that if I fix theta 1, then the other integrals I could do, but then the integral over theta 1, I have to be careful not to just ignore this. Okay, let me do it more carefully. Let me say, this is like computing. I have some integral, and these thetas are in a box of size logarithm of 1 over mx. So this cos, this mx times cos theta is basically 0 everywhere, unless x is huge, and then this suppresses again. So it's like these particles, they are in an integral whose size is log, is when this becomes relevant, is log 1 over mx. So it's a very big box. So basically, the result of this integral is, I can tell you how to do it precisely, but it's the following, is log 1 over mx. Here now I'm using mx very small. That's just the size. And then the integral, the same thing with where you set theta 1 to 0. So you integrate over theta 2 up to theta n. You set theta 1 to 0, and now you can set mx to 0 here. Okay? So it is just, so one way to do it is just call this variable y1, y2, y3, and so on. Then you are left with one variable to integrate. That variable just shows up in the exponent. You do the integral explicitly. It gives some Bessel function. You expand the Bessel function at small mx, you get this log. So that's how you do it rigorously. But intuitively, it's clear. This is just the overall size. So it diverges, and the divergence is proportional to the volume of the box, so it just stands outside.
I mean, in fact, it must be possible to do this integral exactly, right? Because the exact tensor is just a pure power, right? There's no...
At small distances, because it's a free massive boson. It's massive. So at small distances, we get a log. That log is going to be good. But now we get this integral that is a bunch of convolutions. So we can do the convolutions, right? So what is this? Now this was an approximation. Everything here is exact. Is log 1 over mx. Okay. Sorry. Let me write like here. So what is the result that we are getting for this gluing of these two objects? So the result we are getting for the gluing of the objects, right, separated by some distance x, is that this is exponentiated, so it became 1 over mx, because mx is with the log in the exponent. And upstairs, now all these convolutions, it's easy to just go to Fourier, so it becomes d omega over 2 pi, and then I have a sum of an arbitrary number, even number of them, with a 1 over n. So 1 over m sums to log 1 minus the Fourier transform of one of them, which was what I wrote here before, sinh square of pi omega m over 4 minus 1 divided by sinh square of pi omega m over 4. And that would be the final result. Okay, this is the result of doing the cycles, the various convolutions, in a smart way by going to Fourier. Now, I don't know how to compute this integral, at least this morning when I was preparing, so it looks a bit complicated. But we can try to guess what this integral should be. Because what we are saying is that these operators are getting close to each other. So what we should see is that we have this OP, phi m with phi m should be giving phi to m minus 4. So what this number should be, this integral here, is nothing but that delta over there, twice that delta over there computed for m, minus that delta over there computed for 2m minus 4. With, it's a free boson, central charge equal to 1. Okay? So it's some rational function of m that you compute, and then yes, it works beautifully, and it's exactly what this integral gives. So this integral is indeed equal to this expression, which is something like m minus 4. Something like that. And that's precisely what this integral here gives. Okay? So what are we saying? We are saying that in the OP of these two guys, we produce this one, right? And so the dimension, what we get is exactly what we expect from this OP behavior. Okay, so I think I'll stop here for the free boson. Okay, thank you.
Can you use this format? So try to compute the correlation function of this field. But if I think about the original boson, let's call it x, would I compute correlation function of, say, composite operators of x squared, x, three positions, cut it into?
Yeah, we don't know. Yeah, no. So what we see experimentally is that in string theory for vertex operators, this seems to work. So it's not any composite operator, it's vertex operators. You can cut them, and there seems to be some understanding of what this cutting is. For composite operators, not. Yeah, for composite, yeah, I don't know how to do that. Yeah. We could construct the topologies, but I think the precise way of how to rephrase those computations in this language, I think would be very nice, but I don't know how to do. I don't know if Shot has some comments. No. I can just make one comment, which is a bit related to that, which is that when we have the pair of pens here, one thing was to cut over this line, and that's what we just did. So this is what I was just explaining for the free boson. We summed over these states and we got. Something very different, naively, is how do we cut this physical operator, right? How do we cut it into this part, which is here, and this other part that is down here, right? And we could also ask, how do we cut these operators B? What happens when we try to cut these excitations? So our claim when we have a free boson is that when you put the free boson, the free massive boson, the particles can end up on one side or they can end up on the other side. Now, naively, one thing you could do is start with a free boson, put some particles here, and as you are doing this gluing, try to move them around. As this gluing is occurring, you start moving particles around. So it's dangerous because there are all these integrals going on. It's like a factory that and start moving the particles around. And what happens is these particles are moving around, and you are moving this guy around, and your particle can decouple with the mirror particle that was flying there, because there were these poles. So you start moving, and you are integrating here a particle, and it decouples, and it goes here. But then this particle is also on the top, so it gets teleported here. So there is a teleportation mechanism that as you are moving things around, you start seeing that you pick poles or don't pick poles, and they start putting particles in different edges with particular weights. So that sounds like a way that if you have a notion of weak rotation, and if you have some edge that you control, you start moving things around to the region where you are cutting, and as things go around, it's like they get cut as they are moving, and they give you some effective way of cutting the lines where you were indeed cutting, if you want to interpret this as a piece of string and another piece of string. So, okay. Yeah, another comment I would like to make is just that a trivial thing, which is that after we glue, there is no information of where we glue. So there is a trivial statement that I could have glued in any other way. But of course, that's a nice consistency check that we just glued, and that's it. Okay. Okay, so let me then do as promised. So if you remember, the plan of these lectures was to have some pictures, followed by free boson, followed by some discussion of n equals 4. So that's where we are now. Okay? So before, I would like to just conclude what we were discussing before with two small comments about the free boson. One was that I could have decided to change my normalization of my state. Say some particle I multiply by 2. I mean, nothing special. I just like theta by 2, right? When I multiply this theta by 2, then my form factor of theta 1 minus theta 2 would be multiplied by 4. Okay? But of course, that shouldn't change anything. That's just normalization of my state. So how do I get rid of this 4 if I were to put it there? So that's easy, because you remember that when we consider this decoupling limit, where we decouple the particles, right, we say that we just get rid of them. So in that case, when we were to compute the residue of the new f, this residue would be 4. And that would just tell me that now my states, they decoupled. I got the vacuum, which is 1, times 4. So I immediately would interpret this 4 as the normalization of my state. In other words, I would call this 4, I would call it the inverse of the measure mu of theta. Let me just be a bit formal, let me explain. Where now, when I integrate d theta 1, d theta 2, I should always integrate with a measure of theta 1, a measure of theta 2, times the form factor, 0, f, theta 1, theta 2, for example, square, if I wanted to do, say, this loop, times e to the minus, tac, tac, tac. Now, if you decide to multiply the form factor by 5, immediately each measure, the measures would give me 1 over 5, 1 over 5, it would cancel the 5. So this measure is just the normalization of the states. Now, if I decouple them here, or if I decouple them anywhere, it's the same by just boost invariance. So this mu of theta should be equal to mu of theta plus c. That's just boost invariance. But that's because the theory is Lorentz invariant, so this measure is a constant. So, okay, it's just a constant. I set it to 1 and I ignore about it. So if the theory were not relativistic, it's simpler to just keep an open mind, allow for some measure mu, where mu is the residue, is the way the particles, the two particles decouple. You can always make that coupling 1, but it might make your form factors very ugly if the theory is not relativistic. Okay, that's just one comment. The second comment is that when we wrote our form factor, it was a sum of pairs of this f of products of this f of theta I minus theta j. And because f of theta divided by f of minus theta was the S matrix of theta, which was equal to 1, because the S matrix was 1, this had the nice property that if you swap two particles, you get back the same thing with the particle swapped. So I just want you to notice that if S was not 1, that even if I find a function with this property, the same trivial ansatz doesn't work anymore. I swap two particles, there's one term that, yes, gets the right S matrix, but the other terms would just get a big mess. So I just want you to think a little bit that if I have to obey an equation where the S matrix appears, it's really very far from obvious what ansatz you would write. And even more so if you would have indices, because then you are saying that my form factors with index ij is equal to S ij kl form factor with index kl. And that's typically an equation very complicated to solve. So the status about these form factors is that in any theory, computing the form factor for two particles is known and it's easy to do. And for more than two particles, you can do for free boson, free Fermi, and Ising model, and n equals 4. And that's more or less the status, because in practice, the algebra is so complicated that people cannot systematically compute. Okay? So those are the four simplest theories: free boson, free Fermi, and Ising model, and n equals 4. The next to simplest is Sine-Gordon. Okay, so now, yeah, I'm really losing my voice. Okay, so let's go to n equals 4. And in n equals 4, we have indices. We have indices because now a particle, for the free boson, what's the key diff? For the free boson, it was just some particle with some rapidity theta. And now, in n equals 4, the particle can be this excitation that Shota was explaining that transforms under SU2/2 square, and which has some momentum p with a dispersion relation, which is not relativistic, but something a bit more complicated, something like this. Okay? Which also admits weak rotation. You can still replace P by I energy, energy by IP, and get a meaningful weak rotation. But it's no longer relativistic. So this comment about the measure is relevant. When we'll find form factors, we should compute their residue and use it when integrating. That will be a consequence of dealing with something which is not relativistic. And we have indices. Okay? So with indices, the key complication that we will have soon is that when we'll bootstrap the hexagon, we have our hexagon object on the vacuum, and now we have to bootstrap, and the particles have momentum P1 up to Pn, but they also have these indices. So A1 dot to parameterize the first particle, up to an dot. Let's call these two indices joined just I1. And then we have that if I act with S matrix with index I1, I2, J1, J2, U1, U2 on the form factor, on this form factor with indices J1, J2, okay, here U2, U1, I should get the form factor with 2 and 1 exchanged and indices I1, I2. Okay? So graphically, it's exactly the same picture. I have my form factor. It's still drawn here. And I can swap two particles with an S matrix, but now there are indices I, J, K, L, and so on. Okay? So we are dealing now with, so we go from, if we want to use these hexagons to draw this nice picture that I was drawing, here a complication is that we are dealing with a tensor rather than just a number. And so it's useful to think carefully about the symmetries of this tensor in order to fix it completely. Okay? So what we are going to do now is discuss a little bit of symmetry, just a little bit, because Shota did a nice review. And then we have these axioms that we saw the other time, the first, the second, and the third. Remember, it was Watson, decoupling, and monodromy. So the idea is to try to go through this list, and in the end of the day, we will get an expression for what is the hexagon when I insert some particles in the bottom, say. Okay? Okay. So let me just make a comment, which is that when we have the spin chain, we have Z, and we put a particle X, we have Z, Z. So how many how many scalars can we put here? Well, we have X, X bar, Y, Y bar, but we also have Z bar, right? A priori, we could also put Z bar, right? So what happens when I act with Hamiltonian on this state? Remember that Hamiltonian just hops things. So if you act with Hamiltonian, this X just moves with some momentum. It swaps first with a Z, and then it continues to walk. So this excitation just moves as I mix it with the dilatation operator. However, if I put, instead of an X, if I put a Z bar, now, I don't know if you remember, but there is also this term in the Hamiltonian that annihilates these excitations, and it would put this Z bar here. It would annihilate it and produce, for example, an X and an X bar, plus other stuff. Each of which, then, if they start moving away, they never annihilate again. They just move and they hop in the spin chain. So here there is a difference. These guys, we would say they are particles, or this one here as well. These are particles. Whereas this guy, I don't know, something radioactive. Right? We just put it and it touches the vacuum and it explodes into an X and X bar that then move away. So it's not a stable particle. So here we have 4 scalars, X, X, X bar, Y, and Y bar. And there is a symmetry that rotates them. Right? So there is this SU4 symmetry that rotates these scalars. Okay? There is this symmetry that rotates this. No, sorry, SU4 symmetry that rotates these scalars. And so you can think that okay, and let me say one more comment. And then you can also put the derivatives. And there are 4 directions, D1, D2, D3, D4. So there are 4 excitations and 4 excitations here, which was what Schott, in his notation, he was calling these guys, he was thinking of them as bilinears of 2 scalars, 2 mesons where you think as bilinear of 2 scalars. And this guy, where you can think as bilinears of 2 fermions, from the point of view of the indices. It has 2 indices, 1, 2, 2 indices of the first type. This was when we decompose this A as phi 1, phi 2, psi 1, psi 2. And same for the other guy. Okay? And so there is a symmetry that rotates these indices that is smaller than PSU 2,2/4. So we start with 2,2/4. And we go to this SU2/2 square, which is the symmetry, a smaller symmetry, that rotates the particles amongst themselves and kills the vacuum. So this is the symmetry preserved, this was this little group language of Schotta, preserved by the 2-point function background, 2-point function background. When we consider this 2-point function that Schotta was representing with Z to the L, Z bar to the L, 1 say at 0, 1 at infinity. Then the symmetry that kills the vacuum is the symmetry that rotates the excitations among themselves, is this SU2/2 square that was powerful enough to fix the S matrix and the dispersion of these excitations. Now, let's think a little bit about 3-point functions. Okay? So in a 3-point function, the symmetry is broken further because it was already broken a little bit. And now this symmetry, SU2/2 square, gets broken to the diagonal. But let me give you just some intuition of where this symmetry is reduced. So let's consider a 3-point function. So let's put one operator at 0, say Z to the L, one operator at infinity, say Z bar to the L, right? So 0 and infinity are the nicest positions, right? Then we have to put the other guy at 1 always, right? This always poor guy that needs to stay at 1, right? And similarly, z and z bar are already taken. So the analog of being at this crappy position in position space is in R charge. You also need to rotate it somehow. So you can write something like this. And this poor guy, one is at infinity, one at 0. We normally call this guy the reservoir. We like to call it the reservoir, but it is just a picture. You can rotate and make it more symmetrical. And this would be your BPS 3-point function around which you will start now putting excitations. Okay? But now you see that in this picture, this breaks the excitations further. If I put 1 point at 0, 1 point at 1, and 1 point at infinity, there is a difference between derivatives in this direction and the other 3 derivatives in the other directions. So there is now a difference between a d1 and a d2, d3, and d4, where d1 is this direction here, 1. Similarly here, there is a difference between x bar, and y plus y bar, and the other guy, y minus y bar. These ones, I cannot put, if I put any x, there is no way it can be absorbed by any operator, by charge conjugation. So they decouple again into a triplet, and the singlet here that gets here alone. Meaning that I can put a derivative in this direction, I can also put this excitation. Okay? So what's happening is that this part is being broken to a single SU2, out of this SO4, which was SU2 times SU2, like Shota was explaining. And this SO4 is again, or there is some commas, it's again broken to another SU2 by this 3-point function. So the symmetry that remains, if you do everything supersymmetrically, it indeed combines as usual. You just put a slash in between to indicate that it is just a supersymmetric version of it. This is what remains. Now, this is also the symmetry of the hexagon, because the hexagon is the same thing as a 3-point function, just cut in half. It has the same symmetry of the 3-point function. Okay? So this would be the symmetry of the hexagon. It's this diagonal SU2/2. Let me be a bit explicit in what I mean by this. For example, suppose I put here one excitation, just one, in the bottom. Suppose it's a scalar. So if it's a scalar, as we said before, you think of it as a meson of a phi a and the phi a dot, where a is 1 and 2, a dot is 1 and 2. These were the 4 scalars of n equals 4 that I could put written in this SU2/2 square notation. Now, what tensor can I write which uses the indices a and a dot, which a priori I can't write anything because they are different groups, but now I'm preserving only the diagonal? Well, there's one thing I can write. It's just epsilon a dot, the only invariant tensor of SU2. So this tells me that there is one scalar that I can contract this, which is non-zero, that I can put on the hexagon. That's this combination here. Big Y, because it can get out of the reservoir. Any other scalar that I try to contract here with this result would give 0, and I cannot just put one single scalar. I need to put more than one. For derivatives, if it was derivatives instead, let me do a different color. If this was derivatives, then it would be a psi alpha dot, and the same thing, I would say the result needs to be proportional to epsilon alpha dot, which tells me that there is one particular combination, one derivative I can put. The other derivatives, I can't put just one derivative. Okay? Is it clear? So this is the first example of how we see the symmetry in a trivial example, fixing the tensor structure of what is the hexagon with one excitation. It is just a number that tells me which excitations I can put. Okay? Okay, so let me summarize what I just said here concerning the symmetry. So let me make a summary. So as Shota said, each particle has an index A dot, and we can think of it as psi A, psi alpha dot, tensor phi A dot, psi alpha dot. Which particle is like a this SU2/2 square meson. And now the tensors that are allowed under the diagonal, when I put just one particle on a line, if I put, for example, as I said, a particle, which I will draw like this because it has two indices, but this is just one particle, with indices A dot, this would be, for example, epsilon A dot for scalars. Okay? Okay, fine, but that's just one excitation. It's not what we care about. Let's think what we would write if now we want to put two excitations on the hexagon. One excitation has two indices, A dot. One excitation has two indices, B dot. Right? This excitation comes with momentum P. This excitation comes with momentum K.
Can you write a bit bigger?
So this has indices A dot, this has indices B dot. They have momentum P and momentum K. And this object has symmetry SU2/2. So what object did we see today which had four indices and symmetry SU2/2? And depended on two momenta, P and K. The S matrix. And we even said it's unique. Right? So this object should be proportional to the S matrix that depends on P and K, where the only way I can put the indices, A and B, scatter to give the indices A dot and B dot. Or in pictures, this should be proportional to doing the following. We take these indices and we split the indices, the undotted, we split the particle, we split these mesons, the quark, antiquark, we take them apart, and we put the A and the A dot far away. Then we put B and the index B dot far away, and then we just contract them, and this is the S matrix, where this line is associated to P and this line is associated to K. Notice that this picture, there are only two particles, and we take it apart. Now there are four particles and an S matrix, and it's okay. It is just that each particle has two indices, so we get the right number of indices. But notice that this S matrix is not the S matrix of the magnons of n equals 4. The magnons of n equals 4 was this S matrix squared, because we have the left and the right part. Right? So this is like square root of the S matrix of n equals 4. It's like half of the S matrix. Right? And this picture here, this epsilon, was just a contraction. So this object here was also a similar picture where I just take the quark and antiquark and I contract them. Okay? So this starts to be inspiring. We have one example. We have another example that we are starting to guess the structure of what this could be. So based on these examples, we can make a guess for what should be the n particle for what the n particle hexagon should be. Okay, so let's make a guess, and then we are going to check the nice properties. So the guess is that if I want to compute, now if I have, say, three particles, each with two indices, A dot, B dot, C dot, what I do is I take the undotted indices apart, A, B, C. I take the dotted indices here, A dot, B dot, C dot, and I just contract them. And each of these intersections is the S matrix. And the precise guess, let's make, if you want to make a guess, let's be sharp. So if we have the hexagon, the claim is that this is equal to this. Well, but we don't want to say that each weight, the tensor structure, okay, but the precise value might be different. So times a product over I smaller than j of the hexagon function, this is just a function, of ui minus uj, which is just normalizing each intersection. Okay? And this would be the proposal for what these hexagons are in n equals 4. Okay? Now you see, more particles, you just put more lines and intersect, and you multiply more S matrices. Okay? So this object, it definitely has the right symmetry, because it's built out of S matrices that are invariant under SU2/2. But symmetry does not imply this object. I mean, it's not true that this implies this structure here. It allows, for 2 to 2, it's okay. For 2 particles, it does. But for more particles, not yet. So it's...
Here it's essential that this S matrix obeys Yang-Baxter.
Very good. That's a very good point. So for this construction to make sense, if I don't want to worry about how to connect the lines, it's crucial that this S matrix here obeys Yang-Baxter. Because what João is saying, that I could connect the lines. If I'm just saying that I have to connect them, let's try to connect like this. I hope this is going to work. Where you see now this line crosses before it crosses here. Now it crosses first, and then these two intersect. And what's the difference between this product here and this product here is exactly Yang-Baxter. You go from here to here using Yang-Baxter. Right? I remind you, Yang-Baxter is this condition, right? Allows you to move a line, to just drag lines around. So you just take this line and drag it past. Okay? So good. So Yang-Baxter here means that at least the definition makes sense. It allows me to define this proposal. But now, what we should check, so first let me say that, as I said, symmetry does not fix it completely. We suspect that probably some version of Yangian symmetry should fix it completely, but people did not work this out exactly. Okay? But that's an open problem. But the second step we should see is what about the axioms? We said these axioms were hard to satisfy. Now, based on symmetry, we wrote the result right away. It's important to check that we have these nice axioms that of annihilation and so on, because a priori they could fail right away. Okay? So I think it's quite nice to see how they work, because it's different from the way they work is different than in the free boson. So let's check the first one, which was this Watson axiom. Okay, the Watson should be written somewhere here. I multiply by the S matrix, and I should flip the two particles when I do it. Right? Now, what does it mean to multiply by the S matrix? Let's do it on some example, say on that example. And this is particle 1, 2, and 3, and this is 1, 2, and 3. Right? The indices of particle 1, I remind you, are here. This is one index. This is another index of particle 1. This is the indices of particle 2, right? I open them up, and these are the indices of particle 3. And now we want to multiply by the S matrix that swaps particle 1 and 2. But the S matrix that swaps particle 1 and 2 is 2 copies of SU2/2 S matrix. So what I should do is put 2 S matrices here. This is SU2/2 left, and this would be SU2/2 right. Okay? And now, what we want to do is what we want to use unitarity, which is just S dagger S equal 1, or this equal to this, that allows me to take this S matrix and annihilate it with this one. Right? So I just take, and these become two lines. Okay? So I just take that. But then I did not get exactly the same picture because this one is here. I just pass it by here with Young-Buxton. So if I combine both, what I get is indeed I just move it past, and I just obtain particle 2, particle 1, and particle 3 after multiplying by this S matrix. Right? You see that it was crucial for this that the S matrix was a product of two S matrices. So this is something we couldn't have done in, say, the SO6 sigma model. If we tried to just do it in the SO6, we could not. Okay. We could try in the SO4 sigma model, because SO4 is SU2 times SU2, and the S matrix factorizes into 2. But it's not. It doesn't obey the other axioms that I'm going to write. But here, we could, and it worked well. And it was, here what was crucial was that this is just one S matrix, but the S matrix of my particles is this S matrix square. Good. So this Watson equation is checked. It works. Now, sorry. It was a bit too quick. Because it works, I use these pictures, but in using these pictures, I'm assuming that this vertex here, right? I'm assuming that this vertex is normalized such that this function, when I multiply it, it just gives 1. There is, of course, the issue of normalization. So this works, but it sets an equation. It gives me an equation of how this h of uv over h of vu should be equal to some factor times the scattering, the scalar part that dresses the S matrix of u and v. That, for this to work, it already puts some constraint on this function h. That constraint is not so hard to fix, but it's not enough. But it's one condition. So I need to swap this, it needs to work. Now, we check the second axiom, which was this decoupling. Okay. So let me do it graphically again. So we have, say, 4 particles. Let's do, for example, let's do 4 particles just to be fun. Okay. So we just connect them. Okay, and we multiply a bunch of S matrices. And now what we want to do is take this particle, theta 1 and theta, let's say, P2 and P1, and we want to do 2 weak rotations, and then send P1 to P2 to make this particle-antiparticle pair. Now what happens is that when you do it, this S matrix becomes this object, where by this object I mean it becomes a projector into the singlet state. Okay? This is a state which has a particle and an antiparticle with total energy and total charges. Schotter discussed it in this exercise, but I don't know if you discussed it in the lecture, did you? No? So this is a state that you can construct, and it's a useful way of deriving crossing symmetry in theories, which is you construct a state which has 0 energy, 0 color, 0 everything, and you impose that it scatters with everyone else in a trivial way, that it just disappears. When you do it, if you put this singlet state, particle, antiparticle, and you pass an S matrix by it, you derive that the product of S matrices should be trivial, and that's the crossing condition for the S matrices. So exactly this state that's a singlet, it's trivial, and therefore it just decouples and scatters trivially with all these particles, and it just disappears. Yeah. So it is precisely because you produce this singlet state. So you do it, you resolve this, you get this, and then this scatters trivially and just disappears here. And in the end, we end up with just decoupled, and then scattering, and then decoupled here. And this is how the decoupling would work. And for this to work, again, the overall normalization would set another equation for H for the normalization to work out precisely for them to just decouple. Okay. And finally, there is the monodromy that I will just say that it works so that I can have time to mention something else. Uh-huh.
Can you make sense of these broken apart magnons as being actually made of two physical objects? Like, is there some theory of the half magnon?
No, there are some attempts, but no. I think, no, at least not that I know, yeah. But it's tempting, yeah, but no. Okay, so then I would like to conclude now. Okay, so we saw what the hexagon is. We know in principle now how to glue these hexagons together, like we saw in the previous lecture. We just insert, multiply them, put the energies, sum over them, and so on. So what I would like to do, let me write, but I don't know how much time I have. So if you can tell me how much time I have while I write. So what I would like to do is consider one application. Okay. So one application, and then I would conclude with some speculations / open problems. Okay. So this application is a work in progress by my student. Work in progress by Frank Coronado. And I think it's a cute application that allows to test many of the things we saw in Shota's lectures and also in this hexagon business. And what Frank is doing, and I hope that now that it's online he will be pressured to write it up, because I did not tell him that I was going to talk about it, but okay. So he's considering a correlation function, a 4-point function of large operators. So here is what you can do. You can take a correlation function of BPS operators, and let's suppose that one BPS operator is z to the L, where L is large. The other one, let me choose to be z bar to the L over 2, that is some z's connect here. But it's not just z bars, it contains, for example, some x to the L over 2. So the x's, they connect somewhere else. This operator here will be also z bar to the L over 2 and x to the L over 2. So again, the remaining z's connect here and the x's connect here. So this operator would be just x bar to the L. So with this nice choice, it has the advantage that it collapses into the single graph at 3 level. There is a single graph I would draw which has this color assignment. And now, these lines, we take them to be large. Now, I remind you that these lines, if I triangulate my surface, here is one triangulation, like this and like this. Here is 1, 2, 3, 4 triangles, right? And the distance between these triangles, it's actually 0, because there are 0 propagators between this operator and this. This distance here when I glue these two hexagons, is also 0, because there's no propagator here between here and here. But this distance here is some huge distance, because we take the operators to be very large. And because these distances are huge, here, the only thing that can flow is the vacuum. We project out everything else. Right? So all we have to do is glue things along this diagonal, inside and outside. But that's the same thing, so it's just a factor of square. So this becomes just gluing, let me draw diagonally, so I just need to glue these two hexagons, square. And by this gluing, I mean put any number of particles here and integrate over these particles and square it. So the claim would be that if you do this in n equals 4 supreme mills, you are computing this correlation function at any value of the 't Hooft coupling. Okay? And now here comes something nice. Let's try to use what we learned. And let's take this tensor here for the bottom and put one the same on the top to see what we get when we contract these form factors to construct the integrand. Right? But you see that now you can just use unitarity and kill this S matrix with this S matrix. And then apply it consecutively, and this tensor just disappears and gives 1. So all this complication, when I now contract, it just disappear all these tensors, and I get just 1. So it's a huge simplification where this integral actually becomes just a sum over how many particles you have, and then an integral, and the integrand is just this product over I and j of this scalar function ui and uj times the analog of this energy, blah, 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 which is actually where the cross ratios will enter. But I'm not going to discuss this today. So in the end, it is just a very simple integral over these n particles that you insert, a matrix model-like interaction which just interacts like two particles. It looks a little bit like this kind of Vandermonde style things. And if you can resum this particle, this would give you the correlation function for this L large at any value of the 't Hooft coupling. So he computed this, for example, in perturbation theory. You just write this H, expand in perturbation theory, and then Frank computed the expansion of this guy up to 24 loops. Okay? Now you get 24 loop prediction for this function. So what can you do to check these hexagons? You can go to this 24 loop result and you can decompose it in the OP, because this is not OP, as I emphasized several times. So you take this 24 loop data and you series expand it in the OP. And in this way, you get OP data. You get 3-point functions, and you get anomalous dimensions. What you could do then is take all those anomalous dimensions up to 24 loops and solve bit equations that Schotta was writing. What appears really in perturbation theory, it's not one dimension, but a sum of dimensions because you have degeneracy. So what you have to do is you have to solve these bit equations with like 1,000-digit precision, because each solution is a very complicated irrational number. You add them all up to construct these sum rules. You get a nice rational number that you compare with the OP expansion of this function that he computed up to this pornographic number of loops, and it works perfectly. Okay? So that's one, I think, nice application and nice check of this structure. And what we are playing with Frank and Vasco and Thiel Bargier is studying other limits of this object, for example, strong coupling, and even some resummations in N that we can do by just gluing together a few more hexagons. Okay. So I think that's basically it for what I wanted to say about these hexagons in n equals to 4. Let me just conclude with two small comments. One comment is then, what is the general structure, not in this toy model where we had these large operators, but in general? In general is that we have, for example, for a 4-point function, 6 sums. Rather, here it was one sum. It was one sum that was squared, so basically one sum, right? No, one sum. In general, it's 6 sums. And what is being summed are just graphs like this with S matrices, but contracted in complicated ways, where they just don't, it's not just, they don't just disappear, it's one. So the final result is that the 4-point function, or any n-point function, is given by, first you sum over skeletons. For each skeleton, you sum over propagators, how to distribute them in the skeleton. And then for each term, you have an n-fold sum over how to put these mirror particles, where the integrand is some kind of graph where the S matrices are connected in some funny way. So it's some kind of graph, some partition function on some funny lattice where these S matrices are connected, and where the weight of this partition function is the Nicholas S matrix. It's some kind of partition of some kind of statistical mechanical model. And what we desperately need, or one thing we need, is an efficient way of dealing with these complicated partition functions. In the case I spoke about, they just simplify. They annihilate, they give 1. But in general, to realistically construct these integrands and so on, multiplying these tensors, these are big tensors. As you remember, it's, I don't know, 16, but this matrix is big. I forgot it. 4 times 4, 16 by 16. Yeah, it's 16 by 16 dimensional matrix, and we multiply many of them, and so on. So understanding how to resum these particles in an efficient way in general is really something we don't know how to do. However, what is nice is that, say, in perturbation theory, things truncate. As soon as particles need to propagate a few propagators, that already shows up at very high loop order, because each time you propagate one length 1, it costs 1 unit of coupling. So, for example, if you have 3 lines, a particle to propagate from here to here, it takes 3 loops. So if you waste 3 loops putting one particle here, you cannot put particles anywhere else already. So there is some sense in which things truncate, and they are efficient at weak coupling. There is some sense in which at strong coupling, the hexagon becomes 1 plus small correction and exponentiates and makes contact with classical areas. Things also simplify. But at finite coupling, it's still the best we have. It's an infinite sum representation with many n-fold sums. Now, sometimes in some integrable models, that's the best people get to compute, say, correlation functions and of some phi square in sine Gordon of 5 points. You just write many sums, and that's the best you can do. Then you can study some short distance problem or some large distance, but in general, the sums are the best. But we always expect for more in n equals 4, so we hope to be able to resum and to write something even better. And of course, the ultimate speculation is that given the cartoons that I drew in the beginning, I think it should be possible to apply these ideas, say, for string theory in general, and to think of defining some kind of string field theory where the fundamental object is the hexagon rather than the pair of pants. And it would be great if there would be some simplification in trying to do that. And for that, perhaps this more mathematical blah blah that I said in the beginning could be relevant in trying to rewrite known amplitudes like Veneziano and others, where you integrate over moduli as integrals over the other lengths. But that's really speculation. Okay, I'll finish here. Thank you.
Do you have any good reason why the large L is becoming so simple? Is there an explanation, like along the lines of these large charge expansions from these? Do you have some other way of understanding why large L?
In this particular example, the reason why it simplifies is that because you have large L, this piece of string is just a BMN tube. It's just a BPS operator. In practice, if you are here inside with a million neighbors to your left and to your right, everything there is BPS and protected. So there is a separation into a complicated string topology into a simple folded string where one fold of the string is here, and you represent it by drawing all planar graphs you could draw, and the other is the outside. So the surface decouples nicely into a folded string of a square that you just decompose into two hexagons. But it still has most of the richness otherwise. It's not a trivial, it's a very rich function. It still has large spin limits. It still has all these fun limits that we like to play with.
But it's a large R-charge 4-point function, right?
It's a 4-point function of large R charge. But the R charge is not the biggest parameter.
Sorry, it's not?
Here, N is bigger, for example.
Oh, yeah, okay. But it's not like you're in some kinematics.
No, kinematics are arbitrary. Then we can take funny kinematics. And okay, thank you.